Hello everyone, good morning, good afternoon. My name is Matesusz Wojna and I'm pleased to present you the research which I prepared together with my co-authors from Department of Automation, Biomechanics and Mechatronics, Łódź University of Technology. The work is titled Dynamics of Oscillators with Magnet-coil Interaction. My presentation can be divided into a few main parts. Firstly, I would like to familiarize yourself with the considered systems configurations. Then I would like to focus on the 1 degree of freedom model with the emphasis placed on the magnet coil modeling process. Moreover, I want to mention a few words regarding the parameters identification and finally present you the results of the numerical simulations and experimental studies on the 2 degrees of freedom system. The entire system consists of two identical oscillators electromagnetically connected by serial connection of coils. A single oscillator is shown on the left and is a vertically moving mass with the permanent magnets attached at the top and at the bottom. The lower magnet has a repulsive interaction with a stationary magnet in the base, creating the so-called magnetic spring. The top magnet can move near the stationary coil, inducing a current in its circuit. An external load of the circuit, for example a resistor, can be connected to the coil. Dry friction in the system can be neglected due to the use of aerostatic supports for accurate vertical guidance of the oscillator. The mass can be excited by a harmonically moving unbalance driven by a stepper motor permanently fixed to the oscillator. Here a constructed laboratory stand is presented. All control and measurement signals are managed by the National Instrument Data Acquisition Device and LabVIEW software. The oscillator displacement is measured using linear magnetic encoders. In the photo on the right, you can specify the main mass of the oscillator, number 4, and the aerostatic support, number 2, the upper magnet, number 6, interacting with the electric coil 8, and the magnets creating the magnetic spring at the bottom, 5 and 7. Additionally, the stepper motor, number 10, with a fixed arm with the unbalanced mass located at the appropriate radius. Let me move to the mathematical modeling part. Formula 1 presents governed equation of motion of the 1 DOF system. It consists of the components of the magnet-coil interaction Fc and the magnetic spring force Fm. Magnet's interaction is described by the simple expression 2, which parameters F0 and alpha have been determined based on the experimental data. The oscillator has been gradually loaded by known masses and the distance between magnets was successively recorded. Now let me explain in details the process of modeling the magnet-coil interaction, component Fc. Let's consider single conductive ring and moving permanent magnets. Based on the known formulas 3 and 4, the resulting force F, formula 7, can be obtained. Rewritten to the relative forms of equation 5 and 7 have been presented graphically here. When the center of the magnet coincides with the center of the ring, the induced electromotive force is zero and there is no magnetic interaction between them. The maximum electromotive force values, as well as maximum values of the magnetic interaction, are obtained at the position when the magnet is half the distance equal to the radius of the ring on both sides of it. Let me extend the considerations to the n-turned electric coil of radius A and length L, and the permanent magnet approaching it with velocity v. The electromotive force is given by the equation 9, and resulting force can be written as equation 11. Relative values of the induced electromotive force and magnetic interaction force as a function of the dimensionless distance of the magnet from the coil for different values of the sigma parameter are shown in the figures. Sigma indicates the geometric relation to the ratio of the coil's length to the radius. Regardless of the value of the sigma parameter, the value of the induced electromotive force and magnetic interaction force are zero when the moving magnet is exactly in the center of the coil. In turn, the highest values of the induced electromotive force and magnetic force are observed when the magnet passes near the beginning and the end of the coil. In the case of sigma tend to 0, we obtained relationships similar to the curves calculated for a single ring. Based on the previous investigation on the single conductive ring and single layer coil, we have developed final model of the multi-turn and multi-layer coil. In the case of modeling a coil consisting of m layers and n turns each, the electromotive force of induction generated by the entire coil can be determined as the sum of m electromotive forces generated by each of the n-turned coils. Thus, the electromotive force is given by equation 12. Similarly, the principle of superposition can be applied to the magnetic force in the case and resulting in equation 13, where sigma and rho are geometric parameters representing slenderness and rotundity of the coil. Relative relationships of the electromotive force of induction and the force of magnetic interaction are shown in the figures. Exemplary for the sigma equals to 1. As I mentioned at the beginning, the system parameters have been determined experimentally. Masses have been weighted. These magnetic spring restoring force parameters have been obtained based on the static loading tests. It means during this experimental study, no other forces affected the system, only gravitational force and magnetic force between magnets. The expressions for the forces between the coils and the magnet also include a magnetic dipole moment of the magnet, μ. To determine its value, the static tests have been conducted. Through single-layer coil as well as through multi-layer coil, the known constant intensity current has been flowed. As can be seen from equation 16, there is a proportional relationship to the current flowing through coil. As you can see in the figure, for other relative initial positions of the magnet to the coil, the slope of the lines is almost the same. Since the μ parameter is a specific feature of a given permanent magnet, which was the same for all cases, assuming the correctness of the presented model of the interaction of the magnet with coil, its value should be the same for all measurement series, both for single-layer and multi-layer coil. The analogous graphical representation is shown in the figure. Based on the value of magnetic dipole moment has been determined as presented here. Now let me move to the model validation through comparison between numerical simulations and experimental studies. Two upper figures present the ranges of the changes in the position x and velocity of the system in the steady state as the function of frequency f of harmonic inertial excitation. The solid lines in the lower parts of the graphs indicate the minimum values, while the solid lines in the upper parts indicate the maximum values respectively. The blue color of the line has been used for the characteristic determined for increasing excitation frequency, while red color for decreasing excitation frequency. The shaded areas represent all values of position x and velocities x dot between minimum and maximum values. In all cases, a sharp increase in the range of vibrations can be observed, blue dashed line, here and here. As the frequency is further increasing, the corresponding ranges gradually decrease. When decreasing the frequency from 6 Hz to 4 Hz, the range of position and velocity changes gradually increase, the red areas of the graphs. This effect is the result of hysteresis phenomenon occurring in the nonlinear systems. As can be clearly seen, experimental results agree well with the numerical simulations outputs. In the system, we observe also the rapid drop of the vibration amplitude in the nearby of the 4.13 Hz. It is the red dashed line in the graphs. The real behavior of the experimental system can be seen also on the short movie. You can see that right now amplitude is quite high, and with the frequency decreasing, the amplitude is rapidly dropped. This drop has been not only observed experimentally, but also predicted numerically, as presented in the figures. The 1 degree of freedom system has been doubled by second identical oscillator, but second without excitation, and the oscillators have been coupled electromagnetically. The oscillators coil are connected in series. Induced in the first coil current flows to the second coil, resulting the magnet-coil interaction occurrence in second oscillator. The mathematical model is represented by the system of equations 17. We can see the same components as for 1 DOF system, but the magnet-coil interaction forces couple the equations. We used presented before model for multi-turn multi-layer coil. Similarly to the previous study, the correctness of the adopted model has been checked by comparing the amplitude frequency characteristics of the 2 degrees of freedom system. Results show the good agreement between simulations and experiments. For both oscillators, the rapid drops of amplitudes exist evenly numerically and experimentally. You can see the dashed lines. This is the graph for second degree of freedom and the first degree of freedom here. To conclude this talk, it is worth mentioning that the novel model of magnet multi-layer coil interaction has been developed and validated experimentally. I showed also the developed experimental technique of determination the magnetic dipole moment of the magnet, which is usually omitted in other papers. Authors most often provide the specific value of μ without explaining the method of its determination. All of unknown system model parameters have been identified based on the experimental data. Also, it can be stated that the good qualitative and quantitative consistency of the obtained results have been achieved and shown. At the end of my presentation, I would like to play a short movie of the operation of my 2 DOF system. You can see that the left oscillator is excited, but the second one, the right one, is excited only through the coupling, electromagnetic coupling. Some of the presented results have been published in the Journal of Sound and Vibration this year. Thank you very much for your attention.